Okay, so today we're going to be talking about the conservation of mass and conservation of energy. All right. Okay, so with both of these, they're actually more of a unified law. Now, conservation of mass, this was started back when they were doing early chemistry. Conservation of energy was when they were doing early thermodynamics. But both of these were actually unified when Einstein was doing his relativity into what we would now call conservation of mass energy. And this right here is related using the very famous E equals mc squared. So most of you have probably seen that. In this case here, energy is, the E. M is going to be our mass. And this is what we would call the rest mass. And what do I mean by rest mass is that would be the mass when the object is at rest. If you've looked at any special relativity at all, you know that the mass can actually change depending on how fast you're actually going. So this is the mass of the object in its rest frame, which is not moving. And c over here is going to be the speed of light. All right, and the speed of light is approximately 3 times 10 to the 8th meters per second. The rest mass, of course, depends on which object you're actually dealing with, and this is going to be in terms of kilograms. And as long as your mass here is in kilograms, and that's 3 times 10 to the 8th meters per second, this is going to give you your energy in joules. Okay, and that's a very, very common, this is the SI unit of energy here. So this is the E equals mc squared, how the relation between mass and energy. So you can see they are directly proportional to one another, and they're related here by the speed of light squared. Now, for our purposes, when we're dealing with regular chemistry, this very, very small amount of mass gives us a very large amount of energy. And that's why, of course, the speed of light here is extremely large, and you square that, it gets even bigger. So during a normal chemical reaction, you would basically get about a 1 microgram mass change in, and that's a 1 right there, a 1 microgram mass change in about a ton of reaction. So essentially what this means is that if you reacted a ton of material and you weighed the products and the reactants at the end and found out their difference, you would have about a 1 microgram mass change. So essentially you're looking at less than parts per billion changes in mass. And these small mass changes are simply not observable with current equipment. It's simply just too small of a change that other errors would simply creep into there. But if we were dealing with nuclear reactions, in this case, the amount of energy that's released is about 1,000,000 times bigger than that. So if you're dealing with a nuclear reaction, you could actually have on the order of a couple of percent mass change, because the amount that's released in a reaction is actually very big. But that's for nuclear reactions. If we're just dealing with regular chemical reactions, the amount of mass change is insignificant, so we're not going to worry about that. So we're just going to treat here the conservation of mass and conservation of energy separately. So first up, we'll just look here at our conservation of mass, and what does this actually imply? All right, and basically what this implies and what it means is that our initial mass is going to be equal to our final mass. Meaning that if I have some reaction here, so if I have A plus B and it's going to C plus D or whatever, the mass of these reactants over here is going to be equal to the mass of my products, right? So my initial mass of my reactants, final mass of my products is going to be the same. All right, and just to state this very simply, let's say you weigh 150 pounds, and then you eat 1 pound of Oreos. That means you will weigh 151 pounds. All right, so if you are on a diet and you're just wondering, well, how many pounds am I going to eat from eating these cookies? Well, if you eat 1 pound of cookies, the most weight you can actually gain is 1 pound. And if you happen to gain more than that, you've just been eating something else. Okay, so mass is conserved. You're not creating mass out of nothing. And it's one of those things, if you watch any sci-fi, sometimes they have some mysterious alien organism that appears on the ship, and then, its mass quadruples in the period of a few hours. And where is it actually eating? It has to get a food source from somewhere to actually increase its mass. And if you're not getting the mass from somewhere else, well, this thing cannot grow. You need to have, a source of, actual matter to actually make the weight increase. If you're not feeding it, it's not going to grow. And then as for something a little more chemistry related, let's say here I'm taking iron and I'm reacting this with oxygen and I'm making iron oxide. Okay, so that's iron 2 oxide, which is rust. And let's say I'm starting off here with 56 grams of iron, and I end up at the end of the day with 72 grams of iron oxide. Well, then what is this? How many grams of oxygen do I actually have? Well, that's very simply just going to be, if we just look at this as an equation, 56 plus x is equal to 72. Then that means I just have to subtract off my 56 from both sides. And that means that my x here is going to be equal to 16 grams. Okay, so that means 56 plus 16 is going to be 72 grams. Mass is conserved. If we had extra oxygen in there, that would be left over. And when we get to the stoichiometry, we'll see how to do this formally. And also we can start dealing with limiting reagents. What happens if I had 20 grams of oxygen there? Well, you would still get just 72 grams of iron oxide. You would just be left over with 4 grams of oxygen. Okay, so that's a very, very powerful tool that we're going to be using when we get to our stoichiometry. All right, and now next we're going to be dealing with the conservation of energy, and what does that mean? All right, well, this is stated very simply, and this is using the first law of thermodynamics. All right, that energy is neither created nor destroyed in a chemical reaction. We're going to be, now there's several different forms of energy that we're going to be dealing with, but what we're going to look at here is basically 3 things. The total energy, which is right here, this is what we mean by the total energy, and then also kinetic and potential energy. So they're related by this relation here. So the total energy is equal to my kinetic energy plus my potential energy. Now, you may see other things, what about chemical energy or electrical energy? Really, all of these things kind of fall under the category of potential energy, and we'll be exploring that a little bit more detail here. Okay, so right here, the total energy, that's really just the energy of, your whole system. And we're going to be seeing here that this is actually, it all depends on how you actually set your 0 points of there. So we're going to get to this one last, but the first thing we're going to look at here, which is actually kind of the easiest thing, is actually the kinetic energy. So my kinetic energy here is equal to 1/2 mv squared. All right, so the half is obviously a half. M here, this is the mass of the object, and we're just dealing with mass, no rest mass. We're not dealing with this relativistically. So this is just the mass of the object. And here, this is your velocity. And velocity is how fast you're going and where. All right, and basically we can simplify this and say this is the speed, and where you're going, that's the direction. And actually, if we count these 2 terms together here, we would actually count this as a vector. So everyone, should be fairly familiar with speed. You have speedometers on your car. So this is just telling you how fast you're going. So, like 10 meters per second. So it's distance over time. Where you're going is the direction that you're going. So if you're going north or south or east or west, right? So by combining these 2 things, this gives us the velocity. If we just have just how fast we're going, that's just the speed. If we're just doing the direction, that's going to be, just which direction you're going. But by combining these 2 things, we get the velocity here. So my velocity here can be anywhere between negative the c and positive c. And remember from earlier, c is the speed of light. So, and from relativity, we can't actually go over the speed of light here. So the velocity is going to be limited to plus or minus the speed of light. But the velocity here is squared, so therefore this means that my velocity here squared is going to be greater than or equal to 0. And we're not going to be worrying in this class about getting near the speed of light. That's a whole other can of worms we don't want to get into. Basic thing here is that my velocity squared is going to be greater than or equal to 0. That's the main point. As for my mass, the mass here is going to be greater than 0. Okay? I'll actually just write this over here just so we're the same thing here. Now, what would happen if the mass equals 0? That would be in the case of a massless particle like a photon, but actually then we would have a different equation. One of the consequences of Einstein's relativity is that if you have a massless particle, so the mass is equal to 0, the velocity would always be equal to the speed of light. But you would have 0 in the speed of light, and it would technically mean that light doesn't have any energy, but that would be a different set of equations we would actually use from there. So for our purposes, since we're dealing with matter, the mass is always going to be greater than 0. The velocity is always going to be greater than or equal to 0. So by combining these two facts here, this gives us a very simple conclusion that my kinetic energy is always going to be greater than or equal to 0. So you're never going to have a negative kinetic energy here. All right, so that was the first part in the energy equation, the kinetic energy. Fairly simple to actually understand. Next up, we're going to have the potential energy. All right, and this is the energy stored. All right, this is the energy stored because of its location, and all of this potential energy is actually relative. All right, now what does this mean? For instance, this right here is on a table, and if I'm talking about the potential energy, well, if it's at rest here on the table, it has 0 potential energy because it's at its lowest point. But if I raise it up a little bit, well, it's going to have a little higher potential energy. But right now I'm doing this relative to the table. What if I were to switch my position and actually talk about this relative to the floor, or relative to the center of the Earth, or relative to the moon? It all depends on whatever my reference 0 level actually is. So it doesn't matter. Now you might be saying, well, does that mean my potential energy can be anything I want? Yes, but the thing is, once you set where your 0 level is, you have to remain consistent with that. So if I'm doing all my calculations relative to this table here, I have to do that through the entire set of calculations. If I'm doing it relative to the center of the Earth, then I have to stay with that. If I'm doing it relative to the floor, I have to stay with that. So whatever you choose as your 0 point for the potential energy, you have to remain there for the entirety of all your calculations. Now, we dealt with the kinetic energy, and that's fairly easy to understand. The potential energy has many, many different shapes to it, okay? And the reason potential energy is so important is because all things in the universe really desire to be at their lowest potential energy, okay? All right, so all things in the universe desire to be at their lowest potential energy. Now, as for some examples of this, well, let's say you have a bowl. Okay, so here is a little bowl, and I were to put a ball in the bowl. So this ball is going to be in the bowl there, and what's it going to do? It's going to fall down here to the middle, because this is where it wants to be. It wants to go from this high state of potential energy down to a lower state of potential energy. Now what's going to happen is, of course, this ball is going to go back up and go back down and actually oscillate here, and then after it loses some energy due to friction, it's going to fall down to this midpoint. Right? So here I have a bowl, and here I have a little coin. I drop it down here, and where does it go? It goes to the lowest point, right? No matter what I do, and no matter how I move this around, it's always going to fall down to the lowest state of potential energy. So it's always going to do that no matter how many times I actually do this. So that's where it desires to be. Another example is, let's say I have a pendulum. So here it's going to be locked up at this top portion, and then I have this ball over here, and this pendulum is going to go back and forth like this, right? So it's going to, just swing back and forth like this, and it's going to want to be, down here. And eventually, if you have one of those old-fashioned pendulum clocks, when it runs out of its energy, it's going to end up over here, and it's going to be down at the bottom portion. It's at its lowest potential energy again. As for something a little more chemical, if we have here the water molecule, H2O, this actually has a bond angle of 104.5 degrees. All right, so now this water molecule, the reason it's stable in this 104.5 degrees is because if you try squeezing these things closer together, well, now these two hydrogen atoms, their protons, are going to start repelling each other, so that's not going to be good, so they're going to force each other away. And on the other hand, If they try going further away, why not go to 180 degrees? Well, we have actually these lone pairs of electrons up here. So these hydrogens try going out this way. Well, these lone pairs are forcing them down. So really, they're doing the same thing again. They're trying to attain this lowest state of potential energy. And that's why, this molecule has this particular bond angle, because that's where it's happy, where it has its lowest potential energy. If you add energy to the system and start it vibrating, you can have different bond angles here, but it's not going to be happy, and it's going to want to go to this lowest state of energy here. Another one, let's say we have a hydrogen molecule, so H2. Well, this molecule has a bond length between there of 74 picometers, or 74 times 10 to the minus 12th meters. So why does this happen? Well, if you try squishing the protons closer together here, well, they're going to start repelling each other. If you take these further apart, well, then the electron clouds are going to want to set up some net attraction between there with the other protons, and they're going to force them together. So there's actually, an attraction if you get too far apart, and a repulsion if you get too close together. So this is going to form, a stable system that way. And then if you're going into looking at proteins, right? So when proteins are being built, it's a chain of amino acids. You have all these different amino acids all basically linearly organized, and you go from something that looks, maybe like this, and then a chemical reaction happens inside the cell, and you get something which is all squiggled up. And then you get, a functioning protein. And why do you get this functioning protein here is because this straight line of amino acid curls up into its lowest potential energy state and gives you this functioning protein. And actually right here, this is one of the biggest computational puzzles in chemistry and physics currently. Because when you're dealing with these very simple systems here, you can practically just write down the equations and solve them on a piece of paper. Here you're dealing with, hundreds of different atoms, maybe even thousands for the really big ones, and you essentially go from, maybe a two-dimensional problem to some 100-dimensional problem where you're looking at all these little peaks and valleys. So imagine you're looking at a topographical map of the Rockies in the United States, and you want to look where is the lowest energy portion, what has the lowest elevation in the entire Rocky Mountain system. Well, you can't just say, well, I'm going to start at one point and then just walk until I reach my lowest point. Like if we're dealing here with the bowl, I just, move it once and it falls down. But if you're dealing with a very, very complicated system like this, you essentially are kind of like, all over the place here, right? So this, could be how the potential energy looks. So if I start out, over here, well, you fall down and say, okay, well, I can go here. But, you say, well, I'm going here. Well, then you don't know that there is a little portion over here which is at a lower energy. Or if you start out over here, well, you see this gigantic peak, and you're like, well, obviously it's not the way to go, but there's a lower energy peak over here. So you have to, basically sample this entire dimensional, 100-dimensional surface and look for all these potential low points. And, it just happens automatically in the cell, but actually doing this computationally is not an easy problem. And if you can figure out a nice way to optimize this thing, great Nobel Prize work right there. But as for right now, it's very difficult to actually do that. Okay, and the thing is with the potential energy, it really is a driving force into determining how things will actually proceed. So it's fairly accurate to say that the driving force of reactions and just the time evolution of systems is that we're going to be going from an area of high potential energy to an area of low potential energy. And we'll just go through a couple of examples just to kind of demonstrate this. So first off, we can look here at voltage. So if you're dealing with a battery, you have, of course, here, this is a regular AA 1.5 volt battery here. If you're dealing with this battery, of course, it has a voltage. And if there is a particular voltage across here, what's going on is that the electrons are going from an area of high potential to an area of low potential. And this is what, drives the battery. If you measure with a multimeter the voltage across this battery and it comes out to 0 volts, well, then you do not have any potential difference. And really, this is what a voltage is. A voltage is a potential difference. Okay, so a voltage is a potential difference, and if the voltage is zero, there is zero potential difference, you will not get any electrons flowing, you will not have any current, and your device will not work. If you have a voltage, that causes the electrons to flow, all your electronics work. Next up we can look here, and this doesn't have a particular word, but if we just look at the gravitational potential. If I have here my pens a couple centimeters above the desk, it is at an area of high potential relative to the 0 point of my desk, and I lower this down, it will go to an area of lower potential, right? So it's going from an area of high potential to low potential. You do not have to worry about this pen spontaneously jumping up and floating above the table here. So that's what's going to be happening. Also rivers. Okay, so if we happen to look at rivers, the reason that rivers work is because they are going from an area of high elevation, right? So if we just take like a cross section here, so here is, well, let's say the land, right? So here is the land up here, and then it goes out into the ocean. Well, then that means that my river is going to be starting out over here and is going to be going that way. So it's going to be going from an area of high elevation, high potential, to an area of low potential. This is the same reason that certain areas flood. Okay, the water is going to be starting out here, at higher elevations, even though you may only get an inch of rain, but if you're in a very mountainous or hilly location, all the rain that's up here is going to get funneled down to these lower elevations, and down here you can get, several feet of floodwaters, even though you only had an inch of rain. And that's why, sometimes in certain locations, the rivers can go up by several feet, even though you've only had, maybe just a few inches of rain, because you get all this runoff from the land areas flowing into the river that raises it up, because you get much more volume of water coming into a fairly small area over here. And that's why if you happen to be looking for a house, buy up here on the hill rather than down here in the valley, because the water will tend to flow down here, and you're going to get much more likely to be flooded if you're in the valley than if you're up here on the hills. Next up we have chemical potential. All right, and there's actually a couple of different types of chemical potential. There's the enthalpy and Gibbs free energy. We'll talk about these things later in the semester there. But chemical potential really is what drives reactions forward. So if you're taking a sugar molecule and reacting it or burning it to make carbon dioxide and water, you're going to be starting up here with your glucose, which is starting up here, and then it will go over down here to carbon dioxide plus water. Okay. Now the reason that glucose doesn't spontaneously just fall apart into carbon dioxide and water is that there happens to be a little bit of an activation energy here. So it takes a little bit of kick to actually get it to work. All right, for the reaction to actually occur. So, but once you have this activation energy, in other words, like lighting it on fire, then the energy release can self-sustain this reaction and keep it going. Some reactions don't have an activation barrier. They might just go spontaneously. Others, you need this little kick, just like your mom getting you out of bed. You just need that little extra kick to able to get out into the house and do what you need to do. Okay, so that's chemical potential energy. Now, what you might be thinking of, well, wait a minute, carbon dioxide and water, when you put them into a plant, add a little light, you get sugar out. So isn't that going from an area of low potential to making it into high potential? Yes, but you have to remember when this is occurring, you're actually putting in energy to make that happen, right? So you need the sun in order for the plant to make the glucose. You turn the sun off, then the plant is going to die, and it's not going to make any more sugar anymore. All right, and the reason that this can happen is if you're dealing with a plant. So if we have here CO2 plus water makes my glucose, and I have to add in here light to make this happen for photosynthesis. So in other words, if I cut off the light, the plant is obviously not going to make glucose. But really what's happening here with the light that's entering into the system, it's only about 10% efficient. So that means for out of every 10 photons, one of them actually goes into making the glucose. Other stuff is, just keeping the cell running, and there's other losses. And, it's a very, very complicated system, and it's much more complicated than you may have been, told in your high school biology classes. So it's a much more complicated electron shuttling routine with a bunch of proteins in there. But basically, because this isn't 100% efficient, this is why this reaction can actually proceed this way. And to give you an analogy in relating to the river here, if I have my river going like this, well, I can put in here, a water wheel, right? So I can put, as this water's going down the little hill, I can put in a little water wheel. This thing is going to spin. And as this spins, I can extract some energy from it, do some useful work, move rocks or whatever else you need to do. Basically, take something from an area of low potential and moving it up to an area of higher potential. So I can extract some of this energy. Similar down here. As the light is flowing into the plant, some of that light is converted and used to move the carbon dioxide and water to an area of higher potential in the form of glucose. But still, a lot of that light just happens to be wasted and not turned into anything really useful. So really the plant is kind of like the water wheel in this instance. It's extracting energy from the flow of the river of light and using that to make glucose, which is at a higher potential than the carbon dioxide and the water. All right, another thing is radioactivity. So if I have here a radioactive isotope X, it decays into some daughter isotope Y, plus either an alpha particle, a beta particle, or a gamma particle, depending on whatever else comes off of this. Well, if this happens, what we're going to notice here is that this is going to be the high potential energy, and these are going to be the low. And this actually relates back to over here when we were talking about the E equals mc squared. So we're going to be having some change in the mass here, which is going to be lost in the form of energy. And what we're going to find here is that this is going to have a higher mass than this other side. So you're going to be seeing some mass loss, and that mass loss is going to be converted into energy. That energy is going to go into the velocity of these particles as they get shot out. So if you happen to look at, well, why does uranium break apart? Well, that's because the isotopes that it's breaking into have a lower total mass on this side than where we actually started from. Okay, so if you happen to try doing a radioactive decay and these things here are at higher mass than this one, it's not going to decay that way. It simply won't work. So that's why radioactivity happens, simply because it can. Another thing is nuclear fusion. Okay, what keeps the sun shining? All right, so in that case, we're taking 4 protons, and these are being squeezed together at high pressures and high temperatures, and we're getting out here a helium-4 nucleus plus, 2 positrons and 2 neutrinos, which are coming out of there. But basically what's happening is that the mass of all this stuff on this side, this is going to be lower mass than this over here. And this will keep happening. The fusion keeps happening in the star. You keep fusing lighter isotopes to make heavier isotopes until you happen to reach iron. And at that point, you can't actually get any more energy out. And when that happens, the star stops fusing any more elements. It cannot produce any heavier elements via fusion. So there is no more energy that the star can produce. The star implodes, we get a supernova, and then the core either becomes a neutron star or a black hole, depending on its actual initial conditions. So what I said here is that the driving force is going from a high potential to a low potential. And now using the word force here actually is fairly accurate. All right? And the reason for this is that force is related to the change in the potential. All right, and this is expressed mathematically as the negative gradient of my potential. All right, and this little weird upside down symbol right here, it's called a del symbol, but right here, this is really either what you might call a gradient or a slope. Okay. So essentially what this is saying is that, as a function of distance, the potential energy is actually going to change. And if we have this potential energy changing, that is what is reacting and causing a force. Because remember I said that potentials, all they're really caring about is their relative value. So what we're caring about here is the change in that. So right now I have a nice flat table. I put a pen on it, it doesn't move. But if the whole table was tilted slightly, well, then my pen would start rolling off the table, right? So it's obviously fairly level right now, it's not moving, but if I were to lift it a little bit, then the thing would start, rolling on one direction there. And what this is basically saying here is that the more this slopes, the more the potential changes, the larger the force I'm actually going to have on this particle. So we can think about this. Let's say we have here 2 little slopes like this. Okay, so this one versus this one. Okay, so both of these, and what I'm talking about here, this is going to be my distance. So that's my distance. And here's going to be my height. Okay, so you can just think about this, if you're just going up a hill or an inclined plane or something. All right, so both of these have the same height. So the change in potential energy is exactly the same for both of these. But notice that their slopes are different. This one is a much more gradual slope. This one is a much steeper slope. So which is going to produce more force if you try going up this slope? Well, you would think this one, right? Just think about this. If you try walking up an inclined hill or biking up a hill, which is the one that you would actually prefer to go up? You'd want to choose this one. Even though it might take you a little bit longer to do this, but you would feel less force from this one because the change in your potential is going to be much more gradual. So it's going to be much easier to bike up this hill than this hill. And as an extreme example, if I just have this as my hill, well, then, biking up that's going to be basically impossible unless you can jump up really fast, okay? So this is what we're saying is that this is going to, have small force. That's going to be small, and this is going to be a large. Okay, so this is what we're just going to be talking about, in terms of forces, is basically how fast the potential actually changes. So what we can do using this right here is actually get an idea of where and how particles are actually going to interact with one another. So we can draw out here. So right here, this is my energy. So the energy is there on the y-axis, and on the x-axis here is my distance. Now, if I were to draw the potential energy, what this actually looks like, and there's many different types of potential energy, but we're just going to choose a very simple one, the interaction between two atoms. And this is actually fairly typical what it kind of looks like. So what happens out here is if you're at, and right here, this red line I'm drawing here, this is my potential energy. So if you're far away, they really don't feel any force between them because they're far away, they don't know what's really going on. But there's going to be maybe a little slight attraction here. And notice, the way that this is going down, the slope is going down this way, right? So basically, this slope is forcing these particles together. So the force is actually going this way. So there's an attractive force bringing it towards this low point here. At this lowest point, there's actually zero force. There's zero force when you get to that point because at this point it levels out, there's no slope, and it's just like if you take a little quarter and drop it into a bowl, right? I drop the quarter, it's going to fall towards the middle and it stays there no matter which way I actually do this because that's going to be the lowest force, the lowest point in my potential where it levels out and I have zero force. And on the other hand, it's now sloping up quite dramatically here, so my force is actually going to be heading in this direction. All right, so basically when you have the negative and positive forces balance out, you get a 0 point. So this is my potential energy right here. Now let's say we want to figure out, well, how fast is this particle going to be? Now what we could do is use some calculus and figure out the slope. Basically, using this equation up here, figure out the slope of my potential curve and figure out how much it accelerates and then figure out the speed at all these different points. We could theoretically do that, but we can actually do it a little bit simpler. Okay, if you remember from what we talked about earlier here, we said that the total energy is equal to the kinetic plus the potential. So we also remember we said that the total energy is conserved, right? So what this means is my change in my energy is equal to 0. And that is going to be equal to the change in my kinetic energy plus the change in my potential energy. So therefore, the change in my kinetic energy is going to be equal to the negative of the change in my potential energy. Meaning that if I look at this graph up here, my kinetic energy is going to be basically a mirror image of this. So what I can do, assuming that I can draw this fairly easily, is basically say, well, here would be my kinetic energy. So it go like this, then it starts sloping up to about this point where it maximizes, and then it starts coming back down. just like that. Okay, and not exactly the most artistic, but hopefully you get the point. Okay, so that's basically what the kinetic energy kind of looks like. Okay, so this is going to be my kinetic energy. Now notice here I didn't extend this any further because remember we also said that my kinetic energy here is always going to be greater than or equal to 0. So that means that if this is my 0 point of my energy scale, and the reason we can do that is because potential energy is all relative. So I can set this to whatever. I could set that to 5 and it would be fine. But I'm just setting it to 0 to make our life simpler. But eventually you get to the point here when the kinetic energy basically bounces back. So if I take this, and let's say this was a little ball in here, and it'll go back and forth and back and forth, it would just keep going around and around and around inside of here instead of actually stopping at the bottom. All right, so that's kind of a very interesting fact, is that if I take this little ball, so let's say I have a little ball here, it starts out at this point, and it's going to go here, it's going to get faster and faster, so it's going faster. And then once it gets down here, it's going really, really fast. And then the little ball is going to go up, and then it's just going to start slowing down because it's now going up the other side of the hill. And it's going to keep going, slowing down a little bit until it reaches this point at which it stops, turns around, and then goes back. And then it's just going to keep going back and forth and back and forth and back and forth like this forever. So really, a very interesting implication of this is that two isolated atoms cannot. The important thing here is that two isolated atoms cannot form a molecule. So the question, of course, is, well, how does molecules actually form? Because if you just think about this, two hydrogen atoms, we put them at some distance, they start coming together, they reach this point, they bounce apart, then they basically keep going back and forth and back and forth. They have to lose energy somehow to actually go down here to where the stable point is. And the way they can do that is, think about this. If I have my bowl here, the reason that this goes to the bottom is because of friction. In other words, you need a third body to come into this. So what has to happen is you need some third body, another atom in the system, basically bouncing off over here. So when it's coming up to this point, it hits another atom, gives some of its energy to that third body, and now it has lower energy, so it's only going to be vibrating down here, and eventually bounces into somebody else, and eventually will settle down to this lower location. So two isolated atoms can't form a molecule, but you do need third bodies to actually help form actual molecules in real life. Now, this is actually not so much this is not really a big consideration if we're dealing with atoms on here on Earth, because things are sufficiently dense, there's plenty of stuff to bounce around. But if you're in interstellar space, how does two isolated hydrogen atoms actually form a molecule? Because the collision times between different molecules is on the orders of years. It's very, very rare for them to actually encounter separate atoms because it's so diffuse out in the vacuum of interstellar space. Well, the way they do this is you need little interstellar dust grains. So here is my little dust grain over here. Okay, so there's a little dust grain like this. And what happens is a little hydrogen atom comes along and falls onto the surface and gets adsorbed. Okay, so it basically sticks to the surface of the little dust grain. And it just kind of wanders around the little dust grain because it's just stuck on there. And eventually, weeks, years, centuries later, depending on how diffuse it is, another hydrogen atom comes in and then gets adsorbed onto the little dust grain. And then now these two little dust grains are on, or these two little hydrogen atoms are on there. They're just bouncing around, and eventually they're going to, meet. And when they do, they, fall in love there, right? They will fall in love, and we form there an H2 molecule, right? And then what happens is there's the heat from the reaction that comes off, and now the hydrogen atom is ejected into interstellar space. And this is how hydrogen is actually made in interstellar space, and some more complicated molecules as well. If you're starting off with isolated atoms, you need this little dust grain to act as a catalyst to help form the molecule. Because if you just try forming the molecule from two isolated atoms, it's not going to work because they're just going to bounce back and forth over and over and over again. Now, one thing you may have noticed is that I haven't given any formula for potential energy. Like we did with the kinetic energy, for the kinetic energy, I just wrote down very nicely. I said that, the kinetic energy is equal to 1/2 mv squared. Also for the conservation of mass energy, it equals mc squared, very easy. But I haven't done anything except for perhaps, this formula over here, but still, that's not giving a nice formula for what my potential actually is. And the reason is that there is no generic formula for potential, at least anything that is in any usable form. So the main thing is here that all these potentials depend on exactly what kind of a system you're dealing with. If you're dealing with a fairly simple two-body system, you can actually, just sketch these kind of things out. It's actually fairly easy to do. But if you're dealing with a complicated system like a long chain of amino acids making a protein, it's very, very difficult to actually do that kind of a thing. So instead, what we're going to be more worried about is actually, the shape of the potential. What does it actually imply? And we'll worry about all that, as we go along here. Oh, and I probably should mention, since we are dealing here with the kinetic energy of the system, so of course out here, this is when things are going slow, right? And then over here, this is when it's moving very fast. And then, at this point, this is when things have stopped. Right? So this is, if we just look here, we can, that's kinetic energy. It's also going to be related to the velocity of the particle as well. So this is when things are moving fast. It's now slowing down at this point. Here it's accelerating. That's what we see over here, right? It's accelerating, it goes down. It reaches its maximum velocity at its minimum potential energy, and then it reverses course, and then it falls down here to the bottom. All right, and one other little thing about the potential energy. So let's just say I have here some kind of a cannon. Okay, so the cannon, is shooting things off. So when the cannon, ejects the little ball that comes up, it's going to follow, a little ballistic trajectory. So it's kind of like a parabola. Well, when it's at this point, we're going to have here high kinetic energy, and this is going to be low potential energy. All right, because it's close to the ground, so it has a high kinetic energy because it's just been ejected from the cannon, so it's going fairly fast. And then at this point in the middle, we're basically going to have moderate or mid kinetic energy, and then also mid potential energy. All right, and then once it gets up to the highest point over here, we're now going to have the low kinetic energy, and we're going to have a high potential energy. All right, so what's happening here is that the kinetic energy is being transferred into potential energy, and then as this starts falling down again, well, then when we get to this midpoint again, that's going to be the same thing. Because we're at the same height, we'll theoretically have the same velocity. So that's going to have the same kinetic energy, same potential energy at this midpoint. And then once the ball reaches the ground, again, this is going to be exactly the same. We're going to have a high kinetic energy here because it's going to be moving very fast, low potential energy because we're going to be near to the ground. All right, and I will stop it there.